Okay, so last time we got through chapter 13, which was gases and gas laws, which again is the subject of the experiment on Thursday. We're going to go here to chapter 14, I think, and after this, we will circle back to 11, I think, after this. But chapter 14 is not too long of a chapter. We're going to talk about liquids and solids, and we're going to talk about some of the stuff it will tie into some stuff that we did earlier on with specific heat. Not sure how much of solids we're going to really talk about, but we'll do the liquid part for sure. So let's talk a little bit about water and its phases. So water obviously is colorless as a tasteless substance. As we talked about a number of times, it at 1 atmosphere pressure will freeze at 0 degrees Celsius. That's its normal freezing point. It will also vaporize at its normal boiling point of 100 degrees. In between 0 and 100 degrees, you have liquid water. As we talked about, it's not really until you get a little bit below 0 degrees that you do sort of transform into fully ice. Not until you're above 0 degrees that you're sort of in liquid. Again, remember, right at 0 degrees, which is that freezing point, melting point, you do have both phases happening at the same time. So you got kind of like ice crystals sort of occurring. The same thing with the boiling point. It's not until you get just slightly above 100 that you fully sort of transition into gas, if you will. And a little bit below 100, you're still, again, in the liquid phase. One of the interesting properties of water is it does hydrogen bond with itself, and what ends up happening is when it does freeze, it will expand, and that's one of the unusual properties about water, as we talked about, I think maybe earlier on as well. The density of ice is actually less dense than liquid water, and the reason for that is, again, when the water molecules come together in the solid phase, they do not have a lot of energy. And what it ends up happening is it creates these really kind of open spaces between the different water molecules. They really can't, because they don't have enough energy, get really tightly close to one another. They're actually much closer because they have a little bit more energy in the liquid phase. And if you just think about density, which is obviously mass divided by volume, because of that extra empty space, it kind of bloats the ice, if you will, and it creates a larger volume. And just think mathematically about it, this number is going to be bigger than the top number, and that's going to result, obviously, in a smaller density than what we see in liquid water, where they actually can get closer to each other. There's not as much big, open, empty space between the water molecules. So ice density is about 0.9. Water is about 1 gram per milliliter, which again is the value that you can use for the density of liquid water when you need it. A reminder, as I think we also talked about in an earlier chapter, density does change with temperature. So as the temperature changes, so does the density of something like water as well. Now, when we talk about phase changes, this is a heating and cooling curve, and this is one for water. So here we have the temperature in Celsius. We have heat being added or removed, depending on which way you're going. So down here we have ice, which is really the solid version, obviously, of water. This kind of blue line is the liquid version of water. And up here on this kind of pink line there is steam, which is the gas version of basically water. And as we just talked about, we see some transitions that occur. And we can see here at exactly 0 degrees Celsius, as we talked about, that is the normal freezing point and melting point. And we can see that the line is actually plateaued. And what that means is the temperature is not changing, but the phase is changing. It's going from solid to liquid, or if you're going the opposite way, liquid back to solid. And again, that's the part where we were just talking about, where you got basically both phases happening at the same time. That's where you got kind of ice crystals. It's not until you get kind of on that line going upwards or the line kind of going downwards that you fully do transition. We see the same plateau happening over here at 100 degrees Celsius, which again is that normal boiling point there for water. Again, you have both phases happening at that point. You have your liquid water and your steam occurring. And again, it's not until you get a little bit below the temperature or above that temperature that you fully transition to the next phases. Now, when we talk about a heating curve, it is going in this direction, going from solid to liquid to gas, right? That all involves energy being put in there, like an endothermic process, I think we talked about. Obviously, if we're going the opposite way, this direction, cooling, going from gas to liquid to solid, that's an exothermic process, as we talked about, right? Energy needs to be released in this case. A reminder in terms of energy, right? If it is a positive number, then it is endothermic. If it is a negative number, it is exothermic. So when we talk about energy, there actually is a certain amount of energy that is required, frankly, just to do that transition, or a transition from one state to the next. One type of energy required to do that is what is known as the delta H of fusion, or the enthalpy of fusion, or the heat of fusion is sometimes referred to. If you remember, delta H is the change in enthalpy that we talked about in chapter 10 when we did energy. So that is basically our change in energy. A reminder again that just like any energy sort of value, if delta H is negative, you got an exothermic process occurring. And if the delta H is positive, you have an endothermic process occurring. So the delta H of fusion for ice is the energy that's needed to go from solid to liquid, or backwards, liquid to solid, not changing the temperature. And again, this occurs at its normal freezing point temperature, melting point temperature for water, that is 0 degrees Celsius. So at exactly 0 degrees Celsius, this is the amount of energy that is required to simply take, for example, ice at 0 degrees and move it to liquid water at 0 degrees, not change the temperature, just change the phase of it. For water specifically, for the delta H of fusion for water, it is 6.02 kilojoules per mole. That is roughly 335 joules per gram, if you want more of a joule and gram sort of version. Now, this works in both directions. So as we go from solid to liquid, it would be, for example, positive 335 joules per gram. If you were going from liquid back to solid, that's an exothermic process. It would be the exact same number, but it would be negative 335 joules per gram. So again, it's the same number regardless of which way you're going. That sign, as we talked about a number of times in terms of energy, is really important to indicate exothermic or endothermic type reaction, but the sign would just be different. There's also a certain amount of energy required to go from liquid to gas, again, not changing the temperature. This would occur, for example, for water at 100 degrees Celsius. That is the delta H of vaporization, or the heat of vaporization, sometimes referred to. And for water, that is, or anything, that is the transition going from liquid to gas, or gas back to liquid. As you can see there, for water, it is roughly 40.6 kilojoules per mole. That is roughly 2,260 joules per gram of water. And again, these are values for water. If you're looking at some other substance, they would have some different values for those. Again, much like the heat of fusion, it works the same way as you go from liquid to gas, endothermic. So that would be positive 2260 joules per gram. As you go from grams back to liquid, that is negative 2260 joules per gram, as it is exothermic. So this is the energy that is required just to do that phase change. You can use it to figure out how much energy you would need. One of the things that we definitely see is it definitely takes a lot more energy to transition from liquid to gas than it does from solid to liquid. If you look at water going from solid to liquid, or either way, it is 335. If for water to go from liquid to gas is 2260. And if you just think about logically the difference between the states, in the solid state, everybody is relatively close to each other, not a lot of energy. in the liquid state, they're still relatively close to one another, but there's a little bit more room for movement. So it doesn't take as much energy to kind of give them a little boost of energy to get them into the liquid phase. But what happens as you go from the liquid phase to the gas phase, everybody's completely broken apart from one another. So that takes a lot more energy to do so. We actually see that on the chart here we were looking at. You can see the line here from liquid to gas is much longer than the line there from solid to liquid. And again, that corresponds to the difference in energy. So what about if you're somewhere along the way here where you are in the same phase but changing the temperature and you want to know how much energy is required to do that? So if you're in the same phase but you change the temperature, that is going to be our equation from the past, Q equals ms delta T. That's going to be our specific heat equation that you would use to calculate the energy. Remember here, Q is heat or energy, units of joules, right? M is mass in grams, S is the specific heat capacity, and that is again our final temperature minus our initial temperature in degrees Celsius, if you remember. One of those throwback ones, right? The specific heat of liquid water is 4.814 there. Joules per gram per degree Celsius. So again, a reminder that if you are using liquid water, you use that 4.184 number. If you're using something that is not liquid water, you have to use the appropriate specific heat capacity. So when you look at this graph, if you are anywhere moving in sort of, let's erase everything I got on here. If you're moving anywhere, actually we'll do this here. If you're moving anywhere where you are going kind of upwards, if you will, and you want to figure out the energy to do that transition, those are all places where you would use your specific heat equation. Now, if you're anywhere where it has plateaued, like here or here, that's going to be either the heat of fusion or the heat of vaporization, depending on where you are at. So that will either be your delta H of vaporization or delta H of fusion. And again, up here, that would be your delta H of vaporization. Right here would be your delta H of fusion. Now, if you want to know the energy required to just go all the way, say from the bottom to the top of this curve, you would do it in steps and add up all the energy together. So if you remember, energy is it's like a state function. Doesn't matter how many steps it takes you to get there. You could add up all the parts there to get to what you need. So let's take a look at one here where we kind of do that just to kind of show you how it goes here. So let's say, for example, we wanted to uh, figure out how much energy is required to change 75 grams of ice at minus 3.5 degrees Celsius to steam at 102 degrees Celsius. So to do this, we could kind of look at our curve here. We're going to start first off at minus 3.5 degrees Celsius, which would be, we'll just call it right around here for sake of argument. So the first thing that we would actually do is take it from minus 3.5 degrees Celsius ice to 0 degrees Celsius ice. So that's going to give us our transition, or move us towards our transition. So that's really our first step up until that point. And let's do our calculation. We'll call it step number 1 here. So at step number 1, we're going to go from ice at minus 3.5 degrees Celsius to ice at 0 degrees Celsius, which is our normal freezing point, melting point. It is in the same phase, right? They're both ice, they're both solid. but we are changing the temperature. So as I mentioned before, when you're in the same phase but change the temperature, that's going to be your specific heat equation here. Q equals ms delta T. So our Q in this case would equal the mass, which is 75 grams. Now it's important to remember that at this point, though, we are in ice, and that is water in its solid state. And unlike in its liquid state, it's going to actually be a different value for the solid state specific heat capacity. And it's something like, I'm just going to go off the top of my head, I think it's something like 2-ish joules per gram per degree Celsius. So it's not that 4.184 number. That is, again, specifically for liquid water. But here it's going to be about 2. We'll go with 2. It's either 2 or 2.03. I think this one's 2, and I think the other one's 2.03. But we'll go with it here. 2 joules per gram per degree Celsius. Again, we want to do final temperature minus initial temperature. In this case, our final temperature is 0. And our initial temperature is minus 3.5 degrees Celsius. That's going to give us 75 times 2 times basically 3.5, 525 joules of energy. So that represents how much energy to take our ice and start to heat it up, basically, right? And we're starting to heat it up to 0 degrees Celsius. First off, any question on that calculation there? We also ended up with a positive value for Q, which makes sense, right? Because we are heating this up, right? So it's an endothermic process, so our energy should be positive in this case. Now, we are now going to be sitting right here at our 0 degrees Celsius. And the next thing that's going to occur is we are going to do the transition from 0 degrees Celsius ice to 0 degrees Celsius liquid water. And that would be this plateau line right here is our next sort of step that's going to occur. And that we'll call it step number 2 here. So if we go back now to our calculation, the next thing that's going to happen, we're going to take it from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. So once again here, the temperature is not changing, but we are changing the phase of it. And that is where the delta H of fusion is going to come into play. Again, that is the energy, as we talked about, to go from solid to liquid, or liquid back to solid. So that is the energy required to do that. So in this case, I still have 75 grams of ice. I'm going to multiply it by the heat of fusion. And I'm going to use the joule number because my other values are in joules. Obviously, you could use the kilojoules per mole, but you would have to convert things to moles. So I'm just going to use this number here. It is an endothermic process, so it's a positive value. So here we're going to cancel out the grams. And the amount of energy, just simply to take your ice at 0 degrees Celsius to ice at or to liquid water at 0 degrees Celsius is about 25,125 joules of energy to do so. Any questions on that one there? So if we continue through here and take a look back at our chart, we are now sitting right here, liquid water at 0 degrees. Our next really transition, as you can see from the map, is we could actually stay with liquid water all the way through here. So this is all liquid water, all the way up, all the way here, liquid water, until we hit really the next big step, which is the boiling point. But before that, that's going to be liquid water all the way up our curve here. And that would be our third step here. And in this case, what we're doing on our third step is we are taking liquid water at 0 degrees. Try that again. 0 degrees Celsius to liquid water at 100 degrees Celsius. So once again, this is the same phase, but the temperature has changed. So to calculate the energy, we go back to our specific heat formula. So we're going to use our Q is equal to ms delta T. Again, we still have the same mass of our water. At this point, though, we are at liquid water, which means we can use our normal having a memory lapse here, but I think it's 4.184 joules per gram per degree Celsius should be the specific heat capacity of liquid water. Again, that is different than the specific heat capacity here of ice. So depending on the phase and where you're at, you do want to make sure you grab the right specific heat capacity. Our final temperature is 100 degrees Celsius minus 0. And that's going to get us here 75 times 4.184 times 100, about 31,380 joules of energy to take my liquid water at 0 degrees all the way up to my liquid water at 100 degrees. Any questions so far? Remember, we do want to end up at 102 degrees Celsius steam. So if we take a look back at our graph, we are now sitting right here. And once again, we're at a transition point. We now need to take our liquid water to steam, right? And that's going to occur right here at this flat line at its normal boiling point. So the next thing that's going to happen is we're going to take it from liquid water at 100 degrees to basically steam at 100 degrees. We're going to do that phase change that's going to occur here. And again, that is going to be kind of step number 4 here, our delta H of vaporization. Again, that is the energy required to do, again, not changing the temperature, but changing the phase. And that would be the 4th step here. We're going to take liquid water at 100 degrees Celsius to steam, which is basically gas at 100 degrees Celsius. So our delta H of vaporization, I again am going to use the joule value since everything else is in joules. So at this point, all we have to do is multiply our 75 grams times our delta H of vaporization, our 2260 joules per gram. And that's going to get us here about 169,500 joules of energy. That is the energy again required to take that liquid water at 100 degrees and transfer it to steam at 100 degrees. As we talked about a second ago, and if you just look at the numbers here, it was about 25,000 to take it from solid to liquid. It's about 170,000 joules to take it from liquid to gas. So you can see a tremendously much more energy required to do that transition because we are completely kind of breaking everybody apart from each other. So it takes a lot more energy to do that. Any questions on that so far? Yeah. I'm going to say, like normal, you need to know the specific heat for liquid water. Perhaps maybe the fusion of vaporization will pop up somewhere if you need it. Those would probably pop up because those are kind of not normal ones. If you want, you could find those again back in chapter 10 is where that table was with the specific heat capacities of that. And but I say for now, you should still know the one you're supposed to know, which is the one for liquid water, that 4.184 number. No, I would think that maybe it would show up somewhere if you need it. Okay. Yeah. At least in this class. I can't promise you in future classes, but at least in this class, it would probably show up. But you still need to know the specific heat capacity of liquid water, though. Okay? Yeah. And probably if you needed the ice or the steam, it would show up there. So, yeah. Okay. So we are right here now. We are actually made the transition to steam at 100 degrees Celsius. And we're almost to where we want. We do want to end up at 102 degrees. So that is going to require one more sort of transition kind of upwards here. And that's going to be number 5 there. And that's basically taking the now steam at 100 degrees to steam at 102 degrees. Since I'm running out of a little bit of room here, I'll go on this page here. What's that? Step number 5. Step number 5 here, we're going to take steam at 100 degrees Celsius to steam at 102 degrees Celsius. Once again, we're in the same phase, but we're changing temperature. So back to our specific heat equation that we used previously. Again, we're going to go with our 75 grams. We do need to use the specific heat capacity of steam. I'm making it up, but I think it's 2.03. Either that or I got that in the ice backwards, but one of them, and they're both about 2. And our final temperature here is 102 minus 100 degrees Celsius. And we'll go 75 times 2.03 times basically 2 in this case. It's going to get us 304.5 joules of energy required to do that little transition. So what do I do now with my 5 different numbers? What I want to do is figure out the total amount of energy required to do all those steps. So the total energy in this case would be basically taking step number 1 plus step number 2 plus step number 3 plus step number 4 and plus step number 5 and adding them all together. So let's just pull those numbers out. 525 for the first one. We got 125 for the second. And third there was 380. And our fourth one there was 169,500, it looks like. 169,500 joules. And lastly, our last 304.5 joules. So if we add all that together, this is going to give us the total amount of energy to take our ice from ice at minus 3.5 degrees Celsius to steam at 102 degrees Celsius. And that's going to give us roughly here 22,683.4.5 joules. And if we want it kind of in kilojoules, maybe something like clean it up a little bit, 227 kilojoules. You could divide that by 1,000 joules is a kilojoule to get there. First off, any questions on any of those steps? Sometimes when you do a problem like this, kind of thinking of it like a curve is a good way to do it. Again, anywhere, as I mentioned earlier, same phase temperature changes, specific heat equation like we used previously in chapter 10. Anywhere where it is the same temperature but the phase changes, you should be using something like a heat of fusion or a heat of vaporization. What would be the difference if this problem was backwards and I started with steam and wanted to end at ice? What is the only thing that changes here? All these numbers become negative. Everything's exactly the same, right? So if you were going in the opposite direction, everything would be pretty much the same except these numbers would change. These guys would switch, which would give you a negative number. This guy would be negative. These guys would switch, which would give you a negative number. This guy would be a negative number. And obviously our last one, these guys would switch, and that would get you a negative number. And that would make sense, right? Because if we were going from steam back to ice, that's an exothermic process, and the energy should be released, and we should end up with a negative value. Here we were going from solid to gas, which is endothermic, so we should end up with a positive value here. Any questions on that there?